So we're going to start thermodynamics. You're going to see that it gets broken up into two chapters in your book: thermochemistry, which I think is chapter 6, and thermodynamics, which I think is chapter 17. So thermochemistry deals with heat and enthalpy, the flow of energy. We can think of it as thermodynamics deals with entropy, back to that heat and enthalpy a little bit, and then spontaneity, whether a reaction will happen or not. Spontaneity doesn't tell me how fast the reaction happens, that's kinetics. Spontaneity tells me if a reaction will happen or not. Energy is the capacity to do work. In physics, we define it as force times distance. In chemistry, we tend to think of only energy gains or loss during a chemical reaction, although when we deal with gases, we'll see pistons move and stuff, and so work is actually done in the physics sense. We got types of energy. We got kinetic energy, energy of motion. We got potential energy. This is stored due to the location of particles or things. In physics, you think of it as a ball up on a hill has more kinetic energy than a ball at the bottom of the hill. In chemical reaction, it deals with how much things want to be together and how close within their bonds. The SI energy unit for energy is the joule. It's 1 kilogram per meter squared per second squared, and if we have a kilojoule, that would be 1,000 joules. It's convenient to use the energy of calories sometimes. Calorie is the energy needed to raise 1 gram of water, 1 degree Celsius, and so that's where this little calorie comes from. It's equal to 4.184 joules, which you'll see is a very important number later in this unit. And there's also this thing called a big calorie. So when you eat those calories from your food, they're big calories, which is really 1,000 little calories. So the energy needed to raise a kilogram of water 1 degree Celsius, or 1 kcal or kilocalorie. When we deal with energy, we have to worry about what's called the universe, and the universe is simply everything. It's the systems and the surrounding, and we always look at the system. And so things can go into the system and things can come out of the system. And an isolated system, which is what we hope for but never really have, neither matter nor energy can come in or go out. But we do deal with different systems. We have an open system. This is like a coffee mug. And you can exchange both energy and matter. So when you have a coffee mug, it's hot and you see steam coming off, so you see matter leaving. You also know that steam's warm, and so your coffee cools off pretty quickly. You have a closed system, just like a coffee mug with a lid on it, but it's not very well insulated. This is where energy can come in and out, or you could maybe blow up a balloon and it gets larger or smaller by heating it up or closing it down, but matter cannot come in and out. And you have an isolated system, which is neither matter nor energy can be exchanged. And so this is like a really good thermos with a lid on, and things just don't move in and out, nor does heat. And remember that we always look at things from the system. So, hey, if we have energy flowing in, that's endothermic because it's flowing into the system. And if we have energy leaving, that's called exothermic. And so those are where important things to remember. So isolated system, nothing comes in and out of. Closed system, only energy can come out of, in and out of it. And an open system, both energy and matter can come in and out of the system. That's thermodynamics in a quick summary.